back, students, to one more session of your GOC chapter. So till now we've been dealing with different topics like inductive effect, hyperconjugation, metamerism also I've taught as a part of isomerism, tautomerism. Then I've also taught you the concept of electromeric effect. Now in this video we'll be learning about the concept of resonance, right? So resonance, particularly whenever you're learning a particular concept, you have to be very clear about the definition. You need to be clear about the rules for writing the resonance. You need to be clear about the types of resonance as well as resonance energy, right? So before we go into the concept, let's first start with the thing. What is that? That is called definition of resonance, right? So basically, whenever I speak about resonance is, it is a process, just like inductive effect, hyperconjugation, which we have seen. First we will start. It is a process. Okay, let us first write, then understand. It is a process. Okay, what are we doing in this process? We are just taking in which a single compound is considered to be a hybrid of two or more canonical structures. Okay, this is one more word which I have introduced. What are we trying to tell? It is a process in which a single compound is considered to be a hybrid of two or more canonical structures. Means we are going to consider one compound where that undergoes delocalization of pi electrons, and finally we show a resonance hybrid also. This whole process is called resonance. Okay, now we'll also see what are canonical structures. So during this process, what is happening? Most important thing is there is, as I said just now, delocalization of pi electron happens here. So remember, whenever your teacher, if you don't remember this paragraph, you can write delocalization of pi electrons. So that is what happens in resonance. So now what are canonical structures we will see. So we have written the first definition. Now let us come back and write what is canonical structures. So canonical structures, the other name given to canonical structures, we can call the canonical structures as contributing structures. We can write like that, contributing structures. You can also call canonical structures as resonating structures. So this is what is your canonical structure, resonating structures. So basically, what are these, right? So what happens is, like, I have a molecule. Let us assume I have a molecule. I have to explain the different properties of the molecule. When I can't represent all the properties of the molecule, what do? I can or that particular molecule I need to understand. Okay, I'll again come back. So when all the properties of the molecule cannot be explained by a single structure, then what do? I start drawing many structures of that. Those many structures are called canonical structures. Once again, when whatever molecule I have to study, suppose I need to explain the properties. If I'm not able to explain with single structure, I'll try to draw different structures and finally explain the properties. Such structures are called canonical structures. So what are we going to write? What are canonical structures? When all the properties of a molecule cannot be explained by what? By a single structure. Then what do? I start representing the molecule. Okay, single structure. Then such molecule is shown by many structures. Okay, many structures. So those many structures are called canonical structures. Hope this is clear. Done. So now I'll be taking you into examples or how to draw resonating structures or how to draw the canonical structures. But before we draw the examples, always remember you need to add some more important concepts based on this. What are they? Definition I have learned. I have learned the meaning of canonical structures. Now I'll be we'll be knowing about how or what are the different characteristics. Whenever you have to draw, what are the different characteristics you have to remember while drawing canonical structures or resonating structures, right? So before we have learned the definition, we have learned what is meant by canonical structures. Now let us write the characteristics of canonical structures, right? So basically the canonical structures, they have difference in electron distribution only. That is the only thing, right? First important, canonical structures have difference in electron distribution. Let me finish off the characteristics. I'll show you with an example also. Electronic distribution only, right? So whenever you're drawing a canonical structures, how are we going to show? The canonical structures are shown by, I'm writing canonical structures as CS, okay? So canonical structures are linked or denoted or shown, okay, that is right, or shown by a double-sided arrow like this. So one canonical structure is linked to the other by double-sided arrow. Then, so in the canonical structures, the important thing is they should be planar or nearly planar. Okay, canonical structures should be planar or nearly planar. These are all the characteristics, right? And important thing is, whenever you're drawing canonical structures, remember total number of paid and unpaid electrons are also same in canonical structures. That is also important thing which you should remember. Okay, yes, total number of paid and unpaid UN. Okay, unpaid electrons are same in canonical structures in CS, right? Fine. Next, the position and arrangement of atoms are same. Means when you're varying, the position and arrangement of atoms should be there in that molecule only. Let us write the fifth point. Position and arrangement of atoms are same in canonical structures. Okay, now we have written so much, isn't it? Let's see what did I write and how should we relate with an example, right? So first, suppose if I take an example, what are we going to do in the example, right? Let me take this CH2 double bond CH single bond CH double bond CH2. What is this one? This is called, first let us count, 1 2 3 4 but. In which position do we have double bond? In first and third position. So this is 1 3 butadiene, correct? Yes, diene. 1 3 means first position, third position there is double bond present. Done. So here I have to draw canonical structures for this. Now I said they're going to be denoted by or represented by the double-sided arrow, isn't it? Yes, when you denote with the double-sided arrow, what's going to happen here? Just see, the first, this double bond, this one is going to shift. Okay, yes, this double bond is going to shift here. Fine. And this double bond is going to shift here. So how does this look when this is when a bond is broken here? What happens to this? This attains a partially positive charge. Okay, single bond CH, double bond has shifted here. This becomes CH, and because this is bond, this attains a partial negative charge. Further, I can draw one more canonical structure to this. How can I draw? The other way. Now this will attain negative charge and this will attain positive charge. So this becomes CH2 means you're shifting, you're dropping this here, you're shifting this here. Then when you're shifting it here, this also becomes minus single bond CH double bond CH CH2. So this is your canonical structure. I told you, isn't it? Canonical structures have the electron distribution. First point right. Then denoted shown by double-sided arrow. That also is right. Then total number of paid and unpaid electrons are the same. Total number of paid and unpaid electrons are the same in all the three. Next we said position and arrangement of atoms are same in canonical structures. It is only represented in that molecule only, isn't it? Now let's take one more example and see. Suppose if I take this example, let me write it as example 2. Right. Suppose I have one more alkene. Alkene is compulsory. Now I am denoting it by Lewis dot. Now count 1, 2, 3, 4, 5, 6, 7, 8. Now I have to draw a canonical structure for this. Immediately put a double-sided arrow here. Okay, yes. So now what happens? This electron shifts, this double bond shifts. What do we get now? I'm going to get minus here. This becomes single bond CH, and Cl has lost, so this attains a positive charge in this way. So this is how you're going to draw the canonical structures or resonating structures. Hope a student it's example with the it's clear with the example. Right, and important thing is all of the structures must have proper Lewis structure. Whenever you're drawing, Lewis structure should be proper. Don't make it just like that. Properly you have to draw and then only rearrange it. Right. So next, what is the criteria for drawing the Lewis structure? What means, or what is the criteria for drawing resonance? So let us write criteria of resonance. When do we draw, means what should we remember, what is important for showing a resonance, or which will show resonance to us? So basically resonance changes bond length, correct? Right, so that means when I take benzene molecule, right, first let us write it changes bond length. What, suppose if I take benzene, C double bond C, the bond length is 1.39 angstroms, and it is an intermediate. This value is an intermediate between C, which is equal to 1.54, and C double bond C, which is equal to 1.34 angstroms. Right? Yes. Next one, resonance energy. Next concept. Next concept which the resonance depends is resonance energy. Resonance energy. So what is this concept of resonance energy? Let's see. Right, so resonance energy, when I speak, it is a difference between the hybrid and the most stable canonical structure. What is that? Resonance energy is defined by, it is a difference in energy between hybrid and most stable canonical structures. Canonical structure. This is called resonance energy. Okay, right, fine. Suppose if I take benzene as an example, I am taking example as benzene. We very well know benzene shows delocalization of pi electron, so it's going to form a resonance hybrid, correct? Right, finally it shows all the canonical structures and then forms a resonance hybrid. So I said the difference in energy between hybrid and most stable canonical structures, I said. Now let us draw one graph related to this. What is this? This shows on the y-axis I'm going to take resonance energy of benzene. Resonance energy of benzene. Done. Yes. On the y-axis I'm going to take total energetic structure. This one would be total energetic structure. Okay, energetic structure. I'm not writing the full form. Right. So I said benzene shows resonance. Correct. It shows different canonical structures. Now let me draw one of the structure of benzene that represented by the pi electrons. This is one canonical structure. Okay, and here one more I'm drawing. Right. So this is a most stable structure of this. Okay. Yes. Now here you have other canonical structures, other canonical structures. Okay, now what is the difference between this one and this one? The difference here is between, I told you, the energy difference between the hybrid and the most stable canonical structures. Most stable canonical structures and the hybrid, that is, here it is 36 kilocalories. So this is called resonance energy. The resonance energy is the difference between the hybrid and the most stable canonical structures. So this resonance energy, means the concept or the criteria is the first one, it depends change in bond length. Next would be resonance energy. Now, what is important thing which you remember? Always remember important concept about resonance energy. The first very important thing here, important thing is resonance energy is directly related to number of canonical structures. Number of canonical structures. First point. Next, resonance energy is directly proportional to stability. Second important thing you have to remember. Resonance energy, see, I said directly related means it will be inversely related to reactivity, isn't it? Resonance energy inversely related to reactivity. Right? Next, resonance energy is equal to expected heat of hydration minus actual heat of hydrogenation. I'm sorry, actual heat of hydrogenation. Okay, this concept is explained in hydrogenation is addition of hydrogen, isn't it? Yes. So these are the factors on which the resonance energy depends. Now, so next important thing, what will happen when what is the use of resonance in benzene? I told you resonance is directly related to stability, isn't it? Right? So because of the resonance, benzene is quite stable. And what does it do? It gives us a lot of electrophilic substitution reaction, isn't it? Where we show I've also shown you the mechanisms of electrophilic substitution reactions. Different types of electrophilic substitution reaction benzene shows due to resonance only. Right? Fine. So next important criteria I have studied. I have studied about the definition. I have taken an example. Correct? Now, what is the next important thing? Let us show the order of stability of different canonical structures. Right? So before I go into that, let us see the types of resonance and come back to that topic so it's clear. Types of resonance. So basically, resonance is of two types. One is isovalent resonance, and the next one is heterovalent resonance. Isovalent resonance and heterovalent resonance. So isovalent resonance means same number. When same number of bonds and same type of charges are present, then it is called isovalent. What is that? Isovalent is when same number of bonds and same type of charges are present. This is isovalent resonance. Suppose if I have to take hetero, my line is not straight, I'm sorry for that, students. When I take heterovalent, hetero means different, isn't it? Right. Iso means same number of bonds and same type of charges. But when it comes to heterovalent resonance, you have to remember different. Hetero means different. When different number of bonds, and charges are present. Okay, let me take the examples now. So in isovalent, when I take the example, I said same number of bonds and same number. Right, let us see here. SO2, NO2, CO3 minus 2. Isn't it? See here, all two bonds. Here, same type of charges, minus 2. Yes, now let us come back to heterovalent. When I take heterovalent, best example is buta 1,3 diene and vinyl cyanide. Both are different. Charges are different and even the number of bonds also are different. Yes, so this is your type of resonance, students. Now let me come back and meet you with the different stability of different canonical structures, taking different examples. Welcome, students. in the previous video, what did we learn? We have learned the concept of resonance. I've taught you what is the definition of canonical structures. I have also taught you why are we, like, what is the use or criteria for showing resonance. I also told you because of resonance only benzene is showing different electrophilic substitution reactions, right? Like sulfonation, Rayleigh-Crafts acylation, alkylation, nitration, all those. Fine. Now we're going to study about a concept called stability of different chemical structures. We will see the stability, what happens when I take a non-polar molecule or when I take a polar molecule. How is the stability? Right. Suppose if I take a non-polar structure, okay, non-polar structure is always more stable than polar structure. Remember that. First important thing, a non-polar structure is always more stable than a polar structure. Polar structure. Right. Let us see the order now. Right. This is a non-polar molecule. Correct. This is more stable than, see this, now this has become polar, isn't it? This is more stable than so remember, charges are apart, so this is less stable. Why is this is less? Okay, this is most stable, this is less stable. What is the reason here? Reason is charges are apart, so less stable. Right? Done. Suppose next thing, if I speak in terms of polar structures, okay, let us see the next one, next stability concept. In case of, I'm taking only in terms of polar structures. Polar structures. Yes. So remember here, greater the number of covalent bonds, greater will be the stability. Next important thing is greater the number of covalent bonds, greater will be the stability. Right? Yes, students, clear? Yes. Now let us take an example. I have two different one. In this example, let's see which is more stable. So I have CH3, C. This is one example. This is one example. Now see which has more covalent bond. This has more covalent bond, isn't it? Triple bond here. So greater the number of covalent bonds, more is the stability. That means in terms of stability, this is only 2. So this is less stable than the other one. Okay, right. Next one. Let's see one more. The canonical structure, in which each atom has octet state is more stable one. Okay, that means whichever canonical structure has more octet configuration, that will be the stable one. Okay, the canonical structure which has octet or 8 electrons will be more stable. That means, suppose if I take an example like this. Now count the number of electrons here. Here 1, 2, 3, 4, 5, 6, 7, 8. Total are how many? 8 electrons. Here 1, 2, 3, 4, 5, 6. Here 6 electrons. So which is more stable? This is whichever has 8 or octet configuration, that is more stable, I said. Let us take one more example and see. Here, next criteria. if I take an example of this, let me take an example and then explain you. N triple double bond N plus. Okay, 1, 2, 3, 4. Yes. Okay, this is in showing canonical structure of this. Let me first finish off and then come back to you, explain you what am I writing. Yes, this will become unstable N plus triple bond plus. So 1, 2, 3, 4, 5. This is unstable. This is most stable. Okay, what do we write? Right. So if the same charges are closer, see here, this is plus, this is plus. If the same charges are closer, the structure will be unstable. If the charges are separated, okay, the charges are separated, see here, in this case, this is minus, correct? So the charges are separated, they are more stable. The charges are close by, they are unstable. So if same charges, write down, if same charges are closer, structure will be unstable. So remember all these things, right? Next important thing which you have to remember, right? So the canonical structure in which positive charge is on the positive atom and negative charge on the negative atom is more stable. That means, suppose, let us write first the canonical structure in which positive charge is on positive atom. Okay, what do we write here? Positive atom, and negative charge on negative atom is more stable. This is more stable. Okay, right. How do we write this? R, C, R. This is plus. Okay, this is minus. How will one more? R, C, R. Okay. Now compare this. I say the canonical structure, both the canonical structures, okay, means here in this case, right, the positive charge on the positive atom, see here, carbon positive and negative charge on negative atom will be more stable. Okay, here in this case this is minus. So carbon 1s2, 2s2, 2p, 2. Right, so positive charge, if it is in the positive atom and negative charge in the negative atom, that is considered to be more stable. This is here, see here, it is reverse order. That's why this is more stable. So let us recollect once again. Whenever you're writing or stability order is, non-polar structures are always stable than polar structures. Point number 1. What is the next important thing? Greater the number of covalent bonds, greater will be the stability. What is the other one? If positive charge is present in the positive atom and negative on the negative, then again it is stable. Next important criteria, we said, if it has octet configuration or 8 electrons present in the structure, then the canonical structure is more stable. Next thing, we said, if the same charges are present, plus and plus, closer to each other, then it is unstable. It should be separated. Charge separation should be there. Then only it is stable in nature. So these are the stability order, students. Let me come back and meet you with the next topic, that is your mesomeric effect.